Representing and solving a maze given an image. What is the best way to represent and solve a maze given an image? Given an JPEG image, as seen above, what's the best way to read it in, parse it into some data structure and solve the maze? My first instinct is to read the image in pixel by pixel and store it in a list, array, of Boolean values, true for a white pixel, and false for a non-white pixel. The colors can be discarded. The issue with this method is that the image may not be pixel perfect. By that I simply mean that if there is a white pixel somewhere on a wall, it may create an unintended path. Another method, which came to me after a bit of thought, is to convert the image to an SVG file, which is a list of paths drawn on a canvas. This way, the paths could be read into the same sort of list, Boolean values, where true indicates a path or wall, false indicating a travel-able space. An issue with this method arises if the conversion is not 100% accurate, and does not fully connect all of the walls, creating gaps. Also, an issue with converting to SVG is that the lines are not perfectly straight. This results in the paths being cubic Bezier curves. With a list, array, of Boolean values indexed by integers, the curves would not transfer easily, and all the points that line on the curve would have to be calculated, but won't exactly match to list indices. I assume that while one of these methods may work, though probably not, that they are woefully inefficient given such a large image, and that there exists a better way. How is this best, most efficiently and/or with the least complexity, done? Is there even a best way? Then comes the solving of the maze. If I use either of the first two methods, I will essentially end up with a matrix. According to this answer, a good way to represent a maze is using a tree, and a good way to solve it is using the algorithm. How would one create a tree from the image? Any ideas? TL, drive. Best way to parse. Into what data structure? How would said structure help/hinder solving? Update. I've tried my hand at implementing what Mikhail has written in Python, using NumPy, as at Thomas recommended. I feel that the algorithm is correct, but it's not working as hoped. Code below. The PNG library is pip.
Here is a solution. Convert image to grayscale, not yet binary, adjusting weights for the colors so that final grayscale image is approximately uniform. You can do it simply by controlling sliders in Photoshop and image in GT, adjustments in GT, black and amp, white. Convert image to binary by setting appropriate threshold in Photoshop and image in GT, adjustments in GT, threshold. Make sure threshold is selected right. Use the magic wand tool with zero tolerance, point sample, contiguous, no anti-aliasing. Check that edges at which selection breaks are not false edges introduced by wrong threshold. In fact, all interior points of this maze are accessible from the start. Add artificial borders on the maze to make sure virtual traveler will not walk around it smile. Implement Breadth First Search, BFS, in your favorite language and run it from the start. I prefer MATLAB for this task. As at Thomas already mentioned, there is no need to mess with regular representation of graphs. You can work with binarized image directly. Here is the MATLAB code for BFS. It is really very simple and standard. There should not be difficulties on implementing this in Python or whatever. And here is the answer.
This solution is written in Python. Thanks Mikhail for the pointers on the image preparation. An animated breadth first search. The completed maze. Note, marks a white visited pixel gray. This removes the need for a visited list, but this requires a second load of the image file from disk before drawing a path, if you don't want a composite image of the final path and all paths taken. A blank version of the maze I used.
I tried myself implementing a star search for this problem. Followed closely the implementation by Joseph Kern for the framework and the algorithm pseudocode given here. As a star is a heuristic search algorithm, you need to come up with a function that estimates the remaining cost, here, distance, until the goal is reached. Unless you're comfortable with a suboptimal solution, it should not overestimate the cost. A conservative choice would here be the Manhattan, or taxicab, distance, as this represents the straight line distance between 2 points on the grid for the used von Neumann neighborhood. Which, in this case, wouldn't ever overestimate the cost. This would, however, significantly underestimate the actual cost for the given maze at hand. Therefore, I've added two other distance metrics: squared Euclidean distance and the Manhattan distance multiplied by 4 for comparison. These, however, might overestimate the actual cost, and might therefore yield suboptimal results. Here's the code. Here are some images for a visualization of the results, inspired by the one posted by Joseph Kern. The animations show a new frame each after 10,000 iterations of the main while loop. Breadth first search. A star Manhattan distance. A star squared Euclidean distance. A star Manhattan distance multiplied by 4. The results show that the explored regions of the maze differ considerably for the heuristics being used. As such, squared Euclidean distance even produces a different, suboptimal, path as the other metrics. Concerning the performance of the A-star algorithm in terms of the runtime until termination, note that a lot of evaluation of distance and cost functions add up compared to the breadth-first search, BFS, which only needs to evaluate the goaliness of each candidate position. Whether or not the cost for these additional function evaluations, A-star, outweighs the cost for the larger number of nodes to check, BFS, and especially whether or not performance is an issue for your application at all, is a matter of individual perception and can of course not be generally answered. A thing that can be said in general about whether or not an informed search algorithm, such as A-star, could be the better choice compared to an exhaustive search, for example, BFS, is the following. With the number of dimensions of the maze, i.e., the branching factor of the search tree, the disadvantage of an exhaustive search, to search exhaustively, grows exponentially. With growing complexity it becomes less and less feasible to do so, and at some point you are pretty much happy with any result path, be it, approximately, optimal or not.
Tree search is too much. The maze is inherently separable along the solution paths. Thanks to Rainman002 from Reddit for pointing this out to me. Because of this, you can quickly use connected components to identify the connected sections of maze wall. This iterates over the pixels twice. If you want to turn that into a nice diagram of the solution paths, you can then use binary operations with structuring elements to fill in the dead-end pathways for each connected region. Demo code for MATLAB follows. It could use tweaking to clean up the result better, make it more generalizable, and make it run faster. Sometime when it's not 2:30 a.m.